I want to start today by asking you to do something that might feel a little weird. I want you to just stop and actually listen to the room you're in. Maybe you hear the hum of a fan, some traffic outside, or, just the sound of my voice. You trust that experience, right?
Yeah.
You assume your ears are capturing the world exactly as it is,
Yeah.
like a high-fidelity microphone.
It's the most natural assumption in the world, and it is also objectively scientifically wrong.
That is a really unsettling premise we're tackling today.
Yeah.
The idea that what we call hearing isn't a recording process at all. It's a generative process. It is, well, essentially a biologically useful hallucination.
Controlled hallucination is the term some neuroscientists are starting to use, and it fits perfectly here. Today, we're doing a deep dive into a really heavy-hitting piece of research by Keith Kluender and Michael Kieft. It's titled Speech Perception Within a Biologically Realistic Information Theoretic Framework.
Which, I have to be honest, is a title that sounds like it was designed to repel casual readers. But once you crack it open, the ideas inside are just wild. The mission of this paper is to dismantle what they call the microphone fallacy.
Exactly. The microphone fallacy is that intuitive belief that the ear just captures sound waves faithfully, sends them up the auditory nerve, and the brain, files them away. But Kluender and Kiefto argue that if our brains actually worked that way, we wouldn't understand a single word. The world would just be an unintelligible wall of noise.
So the roadmap for today is to understand how we turn that noise into meaning. We're going to look at why accuracy is actually the enemy of survival, how our brains use some pretty advanced statistics to clean up reality, and why babies are actually better at hearing the objective truth of the world than we are.
And to get there, we have to start with a concept from physics that really it underpins everything our senses do. It's called the inverse problem.
The inverse problem. Okay, I've seen this mentioned with vision, with optics, but it applies to our ears too.
It applies to any sensory input. Look, imagine you're walking down the street at night and you see a shadow on a wall. It's a 2D shape. Let's say it looks exactly like a rabbit ears, fluffy tail, the whole thing.
Okay, I see the rabbit shadow. My brain immediately says rabbit.
Right. But here is the problem. Logic dictates that an infinite number of 3D objects could cast that specific 2D shadow. It could be a real rabbit. It could be a cardboard cutout. It could be a hand puppet.
Or a weirdly shaped rock at just the right angle.
Precisely.
So the input, the shadow itself, is technically indeterminate. You can't work backward from the shadow to the object with 100% certainty.
You can't. Too many different things could produce the same result. That is the inverse problem. In hearing, the sound wave hitting your ear is the shadow. And for any given sound wave, there are theoretically an infinite number of real-world events that could have created it. A drum, a synthesizer, a falling rock, a vocal cord. If your brain tried to solve for the truth of what caused that sound every single time, it would freeze.
It would just be paralyzed by the infinite possibilities.
Exactly. It would be stuck in a calculation loop while the tiger ate you.
Which brings up a pretty terrifying question.
Yeah.
If my brain can't know for sure what's making a sound, how have I survived this long? Why didn't our ancestors get wiped out because they were, debating if a roar was actually just the wind?
And that is the absolute crux of the author's argument. They make a brilliant distinction here between validity and reliability.
Okay, let's unpack that, because to me those sound like synonyms.
In this context, validity is capital T truth. It's knowing exactly physically what caused the sound. Evolution. It does not care about validity. Evolution cares about reliability.
Reliability being consistency.
Yes. You don't need to reconstruct the physics of the tiger's vocal cords perfectly. You just need a system that reacts the same way to that specific roar sound every single time. It's about maintaining a stable agreement between the organism you and the environment.
So we're trading accuracy for speed. We trade what is the exact frequency of this wave for is this dangerous or is this food?
The objective of perception is not to paint a perfect picture of the world. It is to create a model that allows for adaptive behavior. If you run away from the tiger, your perception was true enough, even if it wasn't a perfect recording.
That makes sense. Survival over physics. But the paper takes this a step further, into math. They argue that to achieve this reliability, our brains rely on information theory. Now, I know Claude Shannon is the father of the digital age, bytes, but how does that relate to my biological brain?
It comes down to how we define information. We usually think of information as, stuff we know. But in Shannon's world, information only exists when there is uncertainty.
Wait, so if I know something's going to happen, it's not information.
Mathematically speaking, no. If I tell you the sun will rise in the east tomorrow, I haven't given you any new information. The probability was nearly 100%. But if I tell you the sun just turned purple, that's massive information. It's highly unexpected.
So high surprise equals high information.
Correct. Now let's apply this to the environment. The authors talk about the statistical structure of the natural world. It turns out nature follows a pattern called 1F noise, or pink noise.
Pink noise, I use that to sleep sometimes. It's like heavy rain or a fan, right?
Exactly. It has more low-frequency energy. But what it means mathematically is that the world is generally predictable. The wind keeps blowing. The stream keeps flowing. The state of the world 1 second from now is usually very similar to the state of the world right now.
So there's a lot of data hitting our ears, but
Yeah.
not a lot of new information.
Right. And biological systems, like us, have a limited energy budget. We can't afford to process every single bit of data. We'd overheat. So we evolved to ignore the predictable stuff. We only record the change.
This reminds me of nose blindness. You know how you walk into your own house and you can't smell it, but you walk into a friend's house and it has this distinct smell.
That is a perfect example of neural adaptation. It's not just you getting used to it psychologically. Your neurons literally stop firing when a stimulus stays the same. You stop feeling your socks. You stop hearing the refrigerator hum. Your brain says, this is predictable, not information. Delete it.
It's basically an aggressive spam filter for reality.
It is. We are wired to detect contrast. We only hear contrast, not absolute sounds. We hear how sounds change relative to the background. And this is where it gets incredibly messy when we start talking about human speech.
Well, that's the thing. When I listen to you talk right now, it doesn't feel messy. It feels clean. I hear words, cat, dog, table. They feel like little distinct bricks of sound.
That is the illusion. That is the hallucination working perfectly. You perceive speech like beads on a string, distinct, separate, but acoustically. If you look at a spectrogram of speech, it's a disaster. It's a smear.
Smear.
It's called co-articulation. When you speak, your tongue and lips are moving so fast that they're already planning the next sound before they finish the current one. The movements overlap.
So if I say the word tool, my lips are already rounding for the oo sound before I'm even done with the T.
Exactly. And if you say T, your lips are pulled back for the E while you're making the T. So the T in tool and the T in T are acoustically completely different sounds.
It's like cursive handwriting, but the ink is wet and you're dragging your hand through it.
That is the perfect analogy. The signal is smeared. For example, take the sound D. Acoustically, the D in the syllable D is completely different from the D in do. The frequencies are different.
But I hear them both as D. I don't hear D version 1 and D version 2. I hear the category.
You do, because your brain is doing something remarkably complex called spectral contrast. It's using the context to rewrite the signal in real time.
So it's looking at the neighbors to figure out who lives in the house.
In a way, yes. The authors cite a classic study that really blows the mind. It involves the sounds da and ga. Now, imagine we synthesize a sound that's right in the middle, an ambiguous sound. Let's call it A.
Okay, so a generic confused syllable, A.
Now, here is the trick. Whether you hear that ambiguous sound as da or ga depends entirely on the sound that came before it. If they put the sound al before it, people heard ga. If they put r before it, people heard da.
That is bizarre. So alga versus arda. Why does the preceding sound flip a switch on the next one?
It goes back to that nose blindness idea in neural adaptation. The sound R has a lot of energy in the lower frequencies. So when you hear R, the neurons in your ear that detect low frequencies get tired. They physically fatigued.
Okay, so my low frequency detectors are taking a nap.
Right. Then comes the ambiguous A sound. Because your low frequency detectors are tired, the brain relatively amplifies the high frequencies of that next sound.
Wow.
And da happens to be a higher frequency sound than ga. So your brain pushes the perception toward da.
That is, wow. It's surprisingly mechanical. It's not a high-level thought process. It's just neurons getting tired.
Exactly. It's like color correction for audio. If you stare at a red wall and then look at a white wall, the white wall looks green, right? Your red receptors are tired. The ear does the exact same thing.
And for a long time, didn't linguists think this was some special language module in the brain, like a speech instinct?
They did. They thought it was special human software. But Kluender and Kiefde disagree vehemently. They point out that this contrast effect happens even with non-speech sounds. You can replicate this da versus gas switch using simple sine waves or buzzes.
So a chinchilla or a quail might
Oddly-
hear the same illusion.
Yes. It's a general property of how auditory neurons work, not some magical language instinct. Our ears are contrast machines.
Okay, so let's look at the scoreboard. We have a world that's mathematically indeterminate. We have a speech signal that is smeared and messy. We have ears that are exhausted and biased. How on earth do we get to crisp, clear communication? How do I know you said bat and not pat?
This brings us to the concept of categorical perception. This is the brain's ultimate solution to the chaos. We essentially digitalize the analog signal.
Digitalize it, you mean? Like turning it into ones and zeros.
Metaphorically, yes. We lump a huge range of messy, smeared sounds into a single category. We decide to ignore the differences within the category and hyper-focus on the differences between categories.
So we stereotype the sounds. We say, you're close enough to a B, so you go in the B box.
We do. And the paper uses a really sophisticated statistical analogy here. Principal component analysis, or PCA.
Okay, I have heard of PCA in data science, but you're going to have to walk us through it in the context of my ears.
Think of it like this. Imagine you have 1,000 photos of people, and you want to organize them. You could look at every single pixel, which would be incredibly confusing. Or you could ask, what are the main directions of difference?
Like hair length, or eye color, or height.
Exactly. Those are your principal components, the vectors that explain the most change in the data. The brain acts like a statistician. It analyzes the messy audio and asks, what are the main vectors that distinguish one meaningful sound from another? It throws away all the subtle details and it just locks onto the big shifts.
It filters out the noise to find the signal. It's compressing the file.
And there's a beautiful, almost poetic quote in the text from the linguists Jacobson and Halley. They say phonemes, those distinct speech sounds, denote nothing but mere otherness.
Mere otherness. That sounds very philosophical.
It just means a B is only a B because it is not a P and not a D. We define sounds solely by how they conflict with other sounds. It is all relative.
If this is all based on statistics and relative patterns, that implies we aren't bored with these categories, right? A baby doesn't come out of the womb knowing what a bee is.
No, they don't. And this is one of the most fascinating parts of this whole deep dive, how infants become native listeners. Because, ironically, babies are actually better listeners than we are.
Better. But they don't understand anything. They just drool and stare.
They don't understand the meaning, but they hear the detail. A newborn is a universal listener. They can hear every phonetic distinction in every language on Earth.
So a baby born in Tokyo can hear the difference between ra and la just as well as a baby in New York.
Exactly. Even though Japanese adults notoriously struggle with that because it doesn't exist in their language. But by 12 months old, that ability is gone. The Japanese baby becomes deaf to the RL distinction.
So learning a language is actually about losing an ability.
Yeah.
It's not just gaining words, it's deleting potential.
It is a pruning process. It's neural Darwinism. There's a famous study by Worker and Lalonde with Hindi. Hindi has two different D sounds, a dental D where the tongue touches the teeth, and a retroflex D where the tongue curls back.
Into my English-speaking ears, I'm pretty sure those would both just sound like D.
Right, you would fail the test. But a 6-month-old baby from an English-speaking home, they can hear the difference perfectly. But test that same baby at 12 months. They can't hear it anymore. Their brain has decided, this difference doesn't predict anything useful in my environment. Trash it.
They're optimizing their software for the local network. I don't need this Hindi plugin. Uninstall.
Exactly. And this pruning helps them solve the problem of invariance. Think about the vowel, ah. A man saying ah has a deep, low pitch. A woman is higher. A child is even higher. To a computer, those are 3 completely different sound waves.
But the baby knows they're all the same vowel.
Yes. Cool studies show that 6-month-olds can ignore the pitch of the speaker. They recognize that the relationship of the frequencies, the vowel identity, is the same. They're extracting the pattern, not the raw data.
And this has to connect to how they learn to talk, too. Because a toddler has a tiny vocal tract. The physics are completely different.
They are. A toddler is a tiny tube. The dad is a big tube. If a toddler tried to match the exact pitch of their dad, they'd fail. It's physically impossible. So instead, they mimic the contrast. They figure out, okay, dad's voice goes up here and down there, and they map that pattern onto their tiny instrument. They aren't mimicking the sound, they're mimicking the math.
That is incredible. It's all ratios.
It's all ratios.
Okay, so we've got babies pruning their brains, hearing contrast, building these statistical categories. But I want to talk about one final illusion. Words.
The illusion of word boundaries. This is the big one.
Right. When I read a sentence, there are white spaces between the words. It's obvious. And when I hear you talk, I feel like I hear those gaps. The deep.
You think you hear those gaps, but that is the hallucination again. In fluent speech, there are virtually no silent gaps between words. Acoustically, the phrase ice cream and ice scream are identical.
Wait, really? There isn't a tiny pause after ice.
None. If you look at the sound wave, it's just one continuous stream of noise. It's a river, not a chain of islands.
So how on earth does my brain know to cut the stream there? How do I know you aren't talking about ice cream? Or that the deep dive isn't one long word?
Statistics again. This comes from the Safran studies. It turns out infants use something called transitional probabilities.
Okay, let's unpack that. Transitional probability.
It's the likelihood of one sound following another. Think about the syllables pre and fitty. In English, if you hear pre, there's a very high probability the next sound is fitty. Pretty, they're glued together.
Okay, pretty, pretzel, pre has some strong friends.
Right. But now think about the phrase pretty baby. The probability of the sound fitty being followed by ba is actually very low. Tai can be followed by anything, pretty dog, pretty car. The statistical connection is weak.
So the brain notices, hey, pre and titty are always together. They must be a unit. But P and Bob barely know each other, so I'm going to put a cut right there.
Exactly. That dip in probability is where the brain inserts a word boundary. And here's the kicker. Babies do this automatically. You can play them a stream of nonsense syllables for just a few minutes, and they will start identifying words just based on which sounds hang out together most often.
This blows my mind.
Yeah.
We think we're learning vocabulary, but we're really just running complex statistical models on sound streams. We are born statisticians.
It really redefines what language is. And this leads to a really interesting theory about dyslexia that Kluender and Kiefde touch on.
Oh, right. Because if reading is mapping sounds to letters, this whole statistical house of cards matters.
Huge implications. We've established that your brain creates a map of sounds phones during that pruning phase. When you learn to read, you have to map those auditory categories onto visual symbols.
Ugh. Sound maps to the letter B.
The theory suggests that dyslexia might not be a visual problem, but an auditory statistical one. Maybe the statistical map of sounds that the brain created is a little fuzzy. Maybe the categories aren't quite as sharp.
So if your internal B category overlaps a bit with your P category, mapping them to distinct letters would be a nightmare.
Exactly. It's a mismatch between the continuous statistical reality of the brain and the discrete, rigid reality of the alphabet.
It really highlights just how physical and biological this whole process is. We aren't just absorbent minds, we're biological filters.
That's the takeaway.
So let's try to summarize this journey. We've covered a massive amount of ground. We started with the inverse problem, the idea that reality is a shadow, and we can't know the source for sure.
So we stop trying to find the truth. We aim for reliability, and we filter that messy reality through pink noise, ignoring the boring, predictable stuff.
And only focusing on change. Then we deal with the physical smear of speech co-articulation. By using context, we hear da or ga based on what came before it.
Color correcting the audio in real time. Then we use categorical perception to shove those messy sounds into clean boxes like B or P based on statistical otherness.
And finally, we hallucinate word boundaries gaps that don't exist because our brains have calculated the probability of which sounds belong together.
That is the deep dive in a nutshell. We are not recording the world. We are actively constructing a model of it.
It really makes you question the nature of the present moment, doesn't it?
It does. And here's a thought to leave you with. If our perception is entirely based on past experience, on these probabilities and predictions we've built up since infancy, are we ever really hearing the present?
We're hearing a prediction.
We are hearing what we expect to hear, corrected milliseconds later by the error signal. You are essentially living in the immediate past, perceiving a controlled hallucination of your own making.
Well, on that absolute existential crisis of a note, thanks for listening to The Deep Dive.
It was a pleasure. Keep listening critically.